Okay, so I want to use this problem to give you some deeper insight and understanding as to what's going on with implicit differentiation, as well as to introduce you to a set of problems called related rate problems, because of course calculus, at least differential calculus, is about rate of change. So we have a square that is increasing. So just imagine a square starting off with side lengths of 0, and it's growing at a rate such that the sides are growing at 2 centimeters per second. And what we want to figure out in this question is the rate at which the area is increasing if the side length is 6. So I'm going to do this numerically first of all, just by estimating what that answer would be. And I've set up different times, 0 to 4 seconds. The side length is going up by 2 centimeters per second every second. And then I can calculate the area from the side length. So I'm going to estimate the change in area with respect to t at x equals 6, which by the way is when t is equal to 3, same thing. And I'm going to do that through a secant slope. So I'm going to take 2 points on either side that are close by. Well, these 2 points aren't especially close by, but they're all we have at the moment. Although we could have worked out 2.9 for time and 3.1 and worked that out as well. But let's just go with what we've got. So the change in area would be 64 minus 16 over change in time 4 minus 2. So that's 48 over 2, which is 24 centimeters squared per second, is the rate at which the area is changing. My rate is positive, which means the area is increasing, which we can obviously see that it is. So now I'm sure you're wondering, could we calculate that rate of change analytically? Now to do that, we're going to need equations to work with. And because my example is relatively straightforward, I can figure out some relationships between the three variables I've got set up. I've got a connection between the side length and the time. The side length is twice the time. I've also got a connection between area and side length. And because I know the relationship between x and t, I could further replace 2t in that spot and get the relationship between area and time. So area is 4t squared. Now, I actually need the relationship between a and time because I want the rate, which is always with respect to time, when the area of the square is increasing at a side length of 6. So if I were to take the instantaneous rate of change of area with respect to time, which is the derivative, I would get 8t. And then if I were to do the rate at the moment when x is 6, well, when x is 6, we can see from our table that time is 3. If I plug that into my derivative, I get 24 centimeters squared, and we're doing the change with respect to time, which is seconds. So it turned out that my estimate for instantaneous rate at 3 was exactly the same as what it actually is. So that's one way of handling finding the rate of change analytically. Now the other thing you might be wondering is, okay, well that's great, but what I had to do to figure that out is I had to get the connection between all of the variables, time and x and area, and then t and area. Is there a way I could do this without having to have quite so many equations to work with? Well, the answer to that is yes, there is. Okay, so what I'm going to do is I'm just going to take the most obvious relationship. Just by reading that question, probably the first thing that would pop into my mind is that there's a connection obviously between area and x squared. Okay? Now time is involved in this question, and as we know there is a relationship between time and x, which we've calculated. But let's just jump right into differentiating this with respect to time. Okay? Remember, time is a variable in the background. Time is related to area, time is related to x, but we don't necessarily need to know what that relationship is to do the derivative. So I'm going to do the derivative of a with respect to time, which is going to be 2x. And remember, since this is to be thought of as a chain rule, x is related to t, I need to do the derivative of x with respect to t, which is dx dt. Okay, so there's the rate of change of A with respect to time. Now the question was to find the rate at the moment when x is equal to 6. Alright, well, I can go 2 times 6. Now the only other thing that I need to figure out or know is what is the rate of side length with respect to t. Well, we were actually told that. We were told that that was 2 centimeters per second. We were told that right in the question, so we can replace that directly into this spot, and guess what? Here comes our answer out in the most convenient way just by differentiating implicitly.